Hi everyone, my name is Adithya and I'm from NVIDIA. And in this talk, I'm going to present our work on CabiNet about scaling neural collision detection for object rearrangement with procedural scene generation. Object rearrangement in unknown cluttered environments, such as in homes and warehouses, is an important open challenge in robotics. First, let's discuss how prior work has typically tackled this problem. The task and motion planning, or TAMP community, have shown amazing results in complex simulated environments. Since it's a planning-only approach, there's no need for expensive data collection in the real world. But unfortunately, TAMP is super restrictive in practice, as it assumes perfect state estimation and computer vision, and it doesn't really work from raw camera observation. Next up, recent embodied AI approaches have scaled up learning in simulation, but it's been challenging to deploy these learned policies in the real world. The recent robotics transformer work from Google has shown impressive manipulation in real kitchen environments, but unfortunately, it requires expensive data collection on the order of requiring like 10 robots of the data set being collected over a year and a half. And as you may have guessed, our approach checks all the boxes, and we're also able to deploy our model in the real world. In a nutshell, here's our contributions. We first scale up synthetic data generation for rearrangement, which is multiple orders of magnitude more than prior work. With this large-scale data, we train our CabiNet architecture, which can be used in diverse environments for fast point cloud-based collision checking and also for generating robot waypoints for rearrangement. Finally, we demonstrate sim-to-real transfer to the real robot. So here I'm going to discuss the details of our approach to rearrangement. As I mentioned, we first generate large-scale synthetic data in clutter, and we learn from over 650,000 scenes and render nearly 2.5 million synthetic point clouds. And once we have these scenes, we generate over 60 billion scene-object collision queries for learning. With this large-scale data, we train our CabiNet architecture, which is a point cloud-based collision model. So CabiNet takes in the partial point cloud observation of the scene, as shown on the top left. And the robot here is only shown for visualization, and it's segmented away from the point cloud. The point cloud is then encoded into an implicit representation with 3D convolutions. This representation of the scene can then be used to predict collisions between the scene and the object. We generate robot trajectories with MPPI and filter them based on CabiNet collision predictions. The model is also used to predict robot waypoints for transitioning in the rearrangement task. So overall, CabiNet is a very fast point cloud-based collision checker, and it takes on average 7 microseconds per query. When we benchmarked it on multiple environments, including like tabletops, shelves, cubbies, drawers, for over 2.5 million collision queries, CabiNet has a nearly 19% improvement over baselines. Now we want to evaluate CabiNet end-to-end in a complete rearrangement task. And we're going to assume access to some prior work for 6-DoF grasping and instance segmentation. So concretely, the rearrangement task entails picking a target object, as shown in purple here, and placing it in a specified support surface, as shown in green. We first quantitatively test all of this in simulation on 60 randomly generated rearrangement problems in completely unknown scenes and objects. And the key results are as follows. CabiNet, first of all, outperforms a traditional pipeline of a global planner and occupancy mapping. It is also significantly faster because CabiNet and MPPI, they're both able to exploit the GPU parallelization. The waypoints predicted by CabiNet are also crucial for the rearrangement task, because without which the performance just drops significantly. And our CabiNet model achieves zero-shot sim-to-real transfer on the real robot, and this is without needing to train on any noisy point cloud real-world data. It generalizes to completely unseen objects and cluttered environments. And here the task is to rearrange objects when the shelf compartments are stacked vertically. Here the shelf compartments are stacked horizontally. We only use a single extrinsically calibrated scene camera for collision detection. We specify the target object to grasp using instance segmentation and a clickable GUI interface. Our cabinet model also generalizes to out-of-distribution environments, such as the shelf and the dishwasher as shown here. And this is an actual IKEA kitchen setup. And for every new environment, we just needed to recalibrate extrinsically our scene camera. And here are some of our failure modes. So first of all, on the left, occlusions can lead to collision when, for instance, the top of the shelf is partially occluded. We can also have collision errors when transitioning between the pick and place poses, such as in the middle. And unfortunately, sometimes the initial grasp can also fail, as shown on the right. So to summarize, we've shown how we can scale up synthetic data generation and then use it to train our CabiNet collision model for rearrangement in the real world. Thanks so much for hearing this talk, and I hope to see you in London in ICRA. Thank you.